What's up? This is Mr. Rodriguez, and in this video we are going to be talking about kinematics when we have a uniformly accelerated motion, or when whatever object we're talking about is experiencing a constant amount of acceleration, because there's a whole lot of kinematic equations that we use specifically for uniformly accelerated motion. Let's talk about it today. So when we restrict our kinematics to motion with constant acceleration, it actually gets easier because the kinematic quantities that we've discussed, like displacement, initial velocity, final velocity, acceleration, and change in time, relate in some very specific ways when acceleration is constant. So those specific ways, I like to teach them to my students as the big five kinematic equations. And of course, these are only true for constant acceleration or uniformly accelerated objects. Number one, we have delta x is equal to 1/2 initial velocity plus final velocity times time. All right. And so what you'll notice about this big five number one is that it does not take into account acceleration. That's pretty interesting, but it is still only true when we have constant acceleration. We have big five number two here, where we start with final velocity and we set that equal to the initial velocity plus the product of acceleration and time. In this case, we are not taking into account displacement in any way. For big five number three, we have our final position is equal to our initial position. And a lot of times you'll see this written where this is already moved over and it's just delta x displacement, plus initial velocity times time plus 1/2 acceleration times time squared. You'll notice that in this relationship, we are not considering final velocity at all. For big five number four, we have our final position is equal to our initial position plus our final velocity times time minus 1/2 at squared. In this case, we are not considering the initial velocity of the object at all. And then for big five number five, we have the square of our final velocity is equal to the square of our initial velocity plus 2 times acceleration times, and this is going to be our displacement, delta x, or final position minus initial position. In this case, we are not considering time at all. So I put this column here because it's actually important to recognize which variable you're not taking into account, because that's how you're going to more quickly recognize which relationship is useful for the scenario. So if you're dealing with a problem that doesn't tell you anything about time and is not asking you to find time, then it's probably going to be true that this big five number five is the most useful relationship to use in that scenario. So knowing which variable is not taken into account at all, as far as the kinematic quantities are concerned, is actually very useful in figuring out which one of these relationships you want to use for your uniformly accelerated motion problem. Let's derive a couple of these really quickly because it's pretty intuitive. For big five number one, this relationship just represents the definition of velocity as we've learned it before. But specifically for velocity under constant acceleration, because if you plot an object's velocity under constant acceleration, what you're going to have is a linear relationship. And when you have a linear relationship, if you find the area underneath this curve, underneath the actual graph of your change in velocity over time, then what you're going to have is the area of a triangle. And that's all you're going to see here for big five number five. It's saying that displacement is equal to the area of the triangle in the velocity versus time graph, 1/2 v naught plus v final times time. All right, so that's the same thing as 1/2 base times height. And so what we're saying here is that by definition on a velocity versus time graph, the area underneath your graph is equal to your displacement. And so that's what big five number one is saying. For big five number two, this relationship just really represents the definition of acceleration. And it's saying that if you have, again, the same graph here, constant acceleration, then your velocity is going to have a linear relationship with time. And the slope of that line is going to be equal to your acceleration. So it's saying that the definition of acceleration is the slope of your graph on a velocity versus time graph. And so you'll notice here that if we say that acceleration is equal to your change in velocity over change in time, and just rearrange that for final velocity, then you'll get big five number two. Pretty easy. So deriving the other three is a bit more involved and kind of maybe for a longer lecture, but we'll come back to it if we have time and when we have the tools for doing that. For now, let's practice using these equations so we know when to use them. So here we have an example, and let me not show you the solution yet. Let's just read it really quickly. An object with an initial velocity of 4 meters per second moves along a straight axis under constant acceleration. So there's that key word there. Now we know we're probably going to be using one of our big five relationships. 3 seconds later, its velocity is 14 meters per second. How far did it travel during this time? All right, so there's a lot of information given. One, we know it's a constant acceleration problem, so we're going to probably be looking to use one of our big five relationships. Another thing it tells us is it tells us what the initial velocity is. That's v sub 0, v sub naught. It then tells us the time that we're dealing with, 3 seconds, a 3-second time period. And then it tells us the final velocity. After the 3-second time period, the final velocity is 14 meters per second. And then it's asking what was the displacement, or how far did it travel during this time. So what I'm going to go ahead and do is I'm going to write down what's given. I'm going to write down what's given, and what was given was that initial velocity, 4 meters per second, the final velocity, 14 meters per second, and the time that it took, 3 seconds. And what's unknown, what we're looking for, is our displacement. The kinematic quantity that is not considered is acceleration. So that's going to point, if we go straight back to our table, for the quantity that's not considered in acceleration, that's going to point to big five number 1. So let's see if that relationship is going to give us what we need. I'm going to write it down here. Big five number 1, where displacement is equal to 1/2 v naught plus v final times t. And yeah, that's exactly why we want to use this equation, because we don't have acceleration, nor are we looking for acceleration. So we want a relationship that doesn't consider acceleration. That said, I'm going to take this relationship and I'm going to plug in what I know. And so I'm going to say that displacement is equal to 1/2 4 meters per second plus 14 meters per second, because that's initial velocity plus final velocity, times our time. And then from here, just a little bit of simplifying, and we'll get that delta x is equal to 27 meters. So I say that the object travels 27 meters in 3 seconds. So let's talk about the structured method that I just used for solving that problem. If we know we're dealing with a constant acceleration problem, we should follow the following problem-solving steps. First, write down which kinematic quantities are given in the problem. Then, identify which quantity you're looking to solve for. That's exactly what we did when we were solving this problem. For number 3, we're going to identify which kinematic quantity is not being considered and use that information to help choose the relevant big five relationship we are going to use to try to solve the problem. From there, write down that big five equation and use it. Use your algebra, use your math skills to solve for the missing variable. Let's try another example. A car that's initially traveling at 10 meters per second accelerates uniformly for 4 seconds at a rate of 2 meters per second squared in a straight line. How far does the car travel during this time? So first off, we know that it is accelerating uniformly, so we know that we're dealing with probably having to use one of the big five relationships. We know the initial velocity because it says that the car is initially traveling at 10 meters per second. We know the acceleration because it says that it's changing its velocity at a rate of 2 meters per second squared, and the units of meters per second squared should always point you to acceleration. And it also tells us the time. It says it's traveling for 4 seconds at this uniform acceleration. The question is asking for how far does the car travel. So again, this question is looking for displacement. So now we're going to take that and we're going to write down what's given. All right. What's given was the initial velocity of 10 meters per second, the time of 4 seconds, and the acceleration of 2 meters per second squared. And it's asking us about displacement. So we need to look for displacement. The kinematic quantity that's not considered here is final velocity. It doesn't say anything about final velocity in the question, nor does it ask what the final velocity is. So I'm going to say that final velocity is not considered here. Final velocity not being considered points to the big five relationship number 3. And I'll write that down here for you, but you can always check back to your table. And that relationship is final position is equal to initial position, which I usually just straight simplify by moving this to the other side as displacement. Displacement is equal to initial velocity times time plus 1/2 acceleration times the square of time. All right. It looks like I have everything except for displacement here, so I can just plug everything I know in and solve for displacement. I don't even have to do any weird algebra because displacement is already isolated on the left side of the equation. So I'm going to plug in 10 meters per second for initial velocity, 4 meters per second for time, 2 meters per second squared for acceleration, and 4 seconds again for time over here. That said, we're just going to calculate that out. We'll get 40 meters plus 16 meters. Make sure you follow how all these units cancel out to where it's just meters again. 40 meters plus 16 meters adds up to 56 meters, so we can say that the car traveled 56 meters in 4 seconds. Now I want to talk about the free fall question. So an object experiencing free fall, like on a planet, especially near Earth, which is going to be generally the most common kind of example, is probably the simplest real-world example of uniformly accelerated motion. So, of course, if we're talking about uniformly accelerated motion, we do have to ignore air resistance, but an object in free fall does experience constant acceleration due to gravity. So, generally speaking, we assume that anywhere within like the lower atmosphere of Earth, the acceleration due to gravity is relatively constant enough for simple physics problems. So near Earth, gravitational acceleration is about 9.8 meters per second squared, and that's true for, like I said, anywhere within the lower atmosphere of Earth. And it always points towards the surface. And in reality, it actually always points towards the center of Earth. But if you're in the air, the straight down is always towards the center of the Earth, so we say that's towards the surface. For this lecture and for future lectures in this series, we're just going to simplify the acceleration due to gravity to 10 meters per second squared, and we're always going to apply a negative sign to it generally. If that changes, it's going to be because we're using kind of a different frame of reference, but generally speaking, because acceleration due to gravity points downward, we're just going to apply negative to that 10 meters per second squared for simplicity. Let's see an example. A rock is just dropped, okay? Dropped, like you're holding it still, so no initial velocity, is dropped from a cliff 80 meters above the ground. How long does it take to reach the ground? Well, let's go over what's given. When we're getting to this kind of problem, there are some things you're going to have to assume, because the question is assuming you know that the acceleration due to gravity is negative 10 meters per second. So it's not going to tell you explicitly that's what it is. It's telling you that because it was dropped off a cliff, then you can assume that the acceleration is equal to the acceleration due to gravity. So we're going to have to write down that we are given acceleration, which in this case is going to be g, lowercase g, which we have set equal to negative 10 meters per second squared. For our initial velocity, we're going to have to put 0 meters per second. And these are the problems where students start to make a little bit of a mistake on, because some of the information that you have to write down as given is not explicitly stated in the question. It's implicitly stated because it said it was just dropped. That means you were holding it steady before you let it go. So you have to assume that the initial velocity was 0 meters per second. It said it was dropped off a cliff above the ground. So you have to assume it's experiencing acceleration due to gravity. So those two things are technically given, even though they were not explicitly told to you. The one thing that was explicitly told to you is that our initial position, or in other words, our total displacement, is going to be 80 meters because we know that the rock is going to drop from the 80-meter cliff down to the ground. The question is, how long does it take to reach the ground? So the unknown here is actually time. So we're given acceleration, initial velocity, and displacement. We're looking for time. The quantity that is not considered here is final velocity. All right, it doesn't ask about final velocity. It doesn't tell you about final velocity. This points again to big 5, number 3. So I'm going to use y instead of x because we're talking about a vertical situation here, but it's the exact same relationship. I'm going to say that delta y is equal to v naught times t plus 1/2 at squared. Now, what's really cool about this problem is that because we know that the initial velocity is 0, we can completely cancel out this term because v naught times t is just going to be 0 times time. That's great. So we got rid of that term. So what we're left with is the fact that displacement is equal to 1/2 at squared. That said, let's take a look at solving for t. I'm going to multiply both sides by 2 so that I can get rid of that 1/2 and divide both sides by a so I can isolate t squared. And then I'm going to take the square root of t squared so that I'm left with t is equal to the square root of 2 delta y over a. And if we plug in 80 meters, and I should have put y here, sorry about that confusion, guys. If we plug in 80 meters for delta y and we plug in negative 10 for a, then we just solve and take the square root, we'll be left with a time of 4 seconds. Let's talk about the problem in which an object is thrown straight up in the air. So what's interesting about problems in which an object is thrown straight up in the air is that we automatically know that the velocity at the object's peak or the object's apex, the highest point that it's going to reach, is 0, okay? We know that the velocity at that point is 0 because at the point of its apex, it is going to stop going up change direction and start falling down. So anytime an object is changing direction, that velocity in that dimension is zero. For that moment, it's zero. So if you think about it for a little bit and you just throw a rock up in the air, it's slowing down as it's climbing higher. And the moment that it starts to fall back down, it just stops. It hangs in the air for just a moment, an instant, and then it starts falling down. So at that moment that it's at its apex, its velocity is zero. So that's one assumption you'll have to make about an object that's thrown straight up. Okay, so let's look at an example. A baseball is thrown straight upward with an initial speed of 20 meters per second. How high will it go? Again, there are a lot of bits of information that are not explicitly told to you in this problem. The baseball is thrown straight upward with an initial speed of 20 meters per second. How high will it go? All right, so you are explicitly told what the initial velocity is, but you're not explicitly told that the final velocity is going to be zero. All right, because if we're looking for how high it will go, we're looking for the moment that it reaches its peak. And at that point, we just said that the final velocity is zero. So we're going to have to write down that in the given section, the final velocity is 0 meters per second. And that shouldn't be 0 meters per second squared. My mistake. It should be 0 meters per second. We're also not explicitly told what the acceleration is, but we're assuming here that we're near Earth and that our acceleration is going to be negative 10 meters per second squared. We are told that the initial velocity is 20. So these are the things that are given. Okay, these are the things that are given. And what's unknown, what we're looking for is how high will it go? That's going to be that displacement. All right. So what's not considered here at all is time. So that's going to point to big 5 number 5. So I'm going to go ahead. You can always check the table, but I'm going to write down what big 5 number 5 is. Big 5 number 5 is the square of my final velocity is equal to the square of my initial velocity plus 2a delta x. All right. And because I'm looking for delta x, I'm going to algebraically solve for that first just to make my calculations later a little bit easier. I'm going to subtract v naught squared from both sides, and then I'm going to divide both sides by 2a, giving me this expression here. V final squared minus v initial squared over 2a is equal to delta x. What's great is that I can go ahead and cancel out this term because I know my final velocity is 0. That leaves me with negative v naught squared over 2a is equal to delta x. If I go ahead and plug in 20 meters per second for v naught and negative 10 meters per second for acceleration, then I'm going to have this quantity here that I can simplify to just be equal to 20 meters, so that I can say the baseball will reach a height of 20 meters. Let's take a moment to look at the problem in which an object is thrown upward off a cliff. So we're not quite to full two-dimensional projectile motion yet, but an object is thrown upward off a cliff and then it falls all the way back down past its initial position all the way to the ground. All right. So if an object is thrown straight upward with an initial speed of 8 meters per second and takes 3 seconds to strike the ground, from what height was the object thrown? Okay. So for this kind of a problem, it can be a little bit tricky to understand conceptually. So we have to set our reference frame and we have to decide where 0 is and what direction is positive. So generally, I'm going to suggest that you set the ground below the cliff to be your origin, the 0 position, and up to be positive, so that acceleration can still be your negative 10, and you're not doing anything different in this problem than you would normally be doing in a different kinematic problem. So, as you can see here, I've kind of drawn the situation. A baseball was thrown directly upward from some height initially, and it's going to reach some apex and fall straight back down to the ground below the cliff. That said, I set up to be positive and the origin to be the base of the cliff, and I'm going to write down what's given. All right, so what's given is the fact that we have an initial velocity of 8 meters per second, and we're also given a time of 3 seconds, okay? The other thing that's not explicitly given, but we have to understand, is that our acceleration is still negative 10 meters per second squared. What it's asking for is what was the height, the initial height of the object? From what height was it thrown from? So that's going to be our initial position, okay? And again, here I'm using y, and x and y are typically used interchangeably. You usually use y when you're talking about some vertical displacement. You usually use x when you're talking about some horizontal displacement. What's not considered here is the final velocity. It's not in the question at all. It's not implicitly or explicitly given, nor is it asked to be discovered. So that's going to point to big 5 number 3, which I have written here. And we're just going to go ahead and solve by plugging in and solving for y naught. So I know that my final position is going to be 0 because the ball is going to come back to the ground. All right. I don't know what my initial position is yet, but that's what we're solving for. And then for v naught times t, I know that's 8 meters per second times 3 seconds. 1/2 at squared, so that's negative 10 meters per second squared times 3 seconds squared. All right, so if I simplify all this just by calculating, I'm going to be left with the 0 meters, which was where my final position is equal to y naught, which is what we're looking for, the initial position, minus 21 meters. So because my initial position is just 0, I can move y naught to the other side, multiply both sides by -1, and I have an initial position of 21 meters. All right, so these relationships are very powerful as long as we set our reference frame properly. The object must have been thrown from 21 feet above the ground. Finally, let's talk about the full two-dimension projectile motion problem. I mean, the problem in which an object is launched at some launch angle from the horizon, from the horizontal ground, into the air. So objects launched into the air near the surface of the Earth are always influenced by the force of gravity. So you can assume that its acceleration is going to be constant, and it's going to be the negative 10 meters per second squared that we're used to. Objects that are launched with some launch angle that's not vertical or horizontal, but some angle theta with the horizontal surface, tend to follow a parabolic trajectory back to the ground because the force due to gravity and acceleration due to gravity are always pushing them back to the ground. Now, since the initial launch velocity typically makes a two-dimensional vector, as you can see here, we have to analyze the horizontal and vertical motions of the projectile separately, because our kinematic equations, our kinematic relationships really only work in one dimension at a time. So we're going to have to analyze the vertical component to the object's motion separately from the horizontal component to the object's motion. Now, remember, projectiles are under constant acceleration due to gravity, and the kinematic relationships from our big five relationships that are most commonly used in the projectile motion problems are this relationship for the horizontal motion. One thing to keep in mind is that v final in the x direction in the horizontal component of the final velocity is always constant, because we're assuming that we're not going to take into account any other external forces other than gravity. So we're generally going to be neglecting air resistance and any other forces that might be acting on the object. So one thing to remember is that acceleration due to gravity only works vertically. It only causes the object to fall vertically. It doesn't actually affect the horizontal motion of the object at all. That said, whatever horizontal initial velocity was launched with, the object was launched with, that's going to be equal to the final horizontal velocity, because nothing is ever going to be affecting it. Gravity is only going to be affecting the vertical component of the object's motion. So this kinematic relationship is the one that we're going to be dealing with most frequently for the vertical motion. It is big five number 3, all right? And also number 1. I believe that was number 1, or was it number 2? Let's take a look again. Yeah, it was number 2, actually. So, yeah, big five number 2. And we're taking into account that the acceleration in the y direction is always your acceleration due to gravity, all right? And of course, the acceleration in the horizontal direction is always just 0. There's no acceleration in the horizontal direction, and that's why our velocities never change, all right? Take a moment to really let this sink in, because we need to have this down in order to solve this problem, because it is a little bit more involved, because there's 2 components to the object's motion. So let's answer the question, how far did the projectile travel? So here's the question. An object is launched upward with a 30-degree launch angle from the ground and an initial speed of 60 meters per second. For how many seconds will it be in the air, and how far will it travel horizontally? Assume it returns to the ground. First off, we need to find out how long it took the projectile to reach its apex. So we're going to start with this relationship here. Now, generally, you should write down what's given and everything like that, but we first need to just discuss what is the process for solving this problem. The process here is finding out how long it took the projectile to reach its apex, because that's going to give us a lot of information for about how long the projectile was in the air, and we need to find that time, because that's what it's asking for how many seconds will it be in the air. Let me tell you something right now. The amount of time that it takes a projectile to reach its apex is the exact amount of time it takes to travel from its apex back to the ground, all right? That said, if we can figure out how much time it took for an object to reach its apex, if we just multiply that by 2, then we have the total time that it took the projectile to reach back to its initial position in the y direction. That said, we're going to go ahead and use Big Five relationship number 2. V final is equal to V initial plus AT, where A is just G. I'm going to rearrange it for time because we're looking for time. And because this is just in the time frame between when the object was launched to the time that it reached its apex, I know that the final velocity is 0. I also know that G is negative 10 meters per second, but we need the initial velocity in the y direction. We were given the initial speed, but at a 30-degree angle with the horizontal, okay? So look at this triangle right here. We were given the initial speed. That initial speed is said to be 60 meters per second. But that is the initial speed in the direction of 30 degrees above the horizontal. We need the speed that is just vertical, the vertical component to that 60 meters per second. So we're going to use a little bit of right triangle trigonometry here. You see this triangle here. If we have a 30-degree angle with the horizontal, then this vertical leg can represent the vertical component to that initial velocity. And we'll find that vertical leg by taking the hypotenuse here, which is our initial velocity of 60, and multiplying it by sine of 30. It's sine of 30 because that leg is opposite from our angle. If it was adjacent to our angle, it would be cosine of 30. But we're not looking for the horizontal component right now. We're looking for the vertical component. So we can now say that the initial vertical component to our velocity is 60 times sine of 30. And you're going to see me calculate that out here. Time is equal to, because we canceled out this term, it's just, it should be negative V naught sine theta, which our V naught was 60, times sine of 30 degrees, divided by our 10 meters per second squared. So this negative sign canceled out because we use negative 10 meters per second squared. Calculate that out, and we find that it takes 3 seconds to reach the apex for this projectile. Now, in orange over here, you're going to see that I made a note. If it takes 3 seconds to reach the apex, then it will take 3 more seconds to fall back down for a total projectile time of 6 seconds. We're going to need that to find our horizontal displacement. So for our horizontal displacement, we're going to use this relationship. Delta x is equal to our initial velocity times time. That said, we know what our initial horizontal velocity was if we come back to our triangle and find out the initial horizontal component. That's going to be the 60 cosine 30 degrees. All right. So I'm going to say 60 meters per second cosine 30 degrees times my total time. Calculate that out in the calculator. We have 312 meters. So we can say that this projectile traveled 312 meters in 6 seconds if it was launched with 60 meters per second initial velocity at an angle of 30 degrees from the horizontal. All right. That problem we went through pretty fast, but go through it again if you need all of those bits to sink in. Remember, when we get into two-dimensional problems, that right triangle trigonometry is always going to come in handy. So make sure you go back and review right triangle trigonometry if you need to. All right, if you feel like you want more practice on this topic, there will be some practice problems assigned to this lecture. Solution videos should be posted, but you can download the questions below. Good luck studying, and I'll see you guys in the next one.